Hello friends, I'm Janaki Ghosh. Welcome to this session which is being conducted as a part of the Mathematics Week from 15 to 22nd December. It is the culmination of the Ramanujan Yatra initiative taken by Vigyan Prasar to commemorate the 100th death centenary of Srinivas Ramanujan. In this session, we'll be exploring the famous Star of Hanoi puzzle, which is an old, popular and celebrated puzzle. It was discovered by Edward Lucas in 1883. Now I'll show you a model of this puzzle. So basically this has a wooden base and there are 3 metallic pegs. And on one of these pegs are arranged 6 circular discs of reducing radii. Here they are of alternate colors. And the puzzle, to solve the puzzle, we need to shift this entire tower from one peg to any of the other 2 pegs using precisely 2 conditions. The first is that at a time, you can only move one disc. So these are legal moves, but you cannot move more than one disc at a time. So you can't do this straight away. The second is, at any given point, you cannot place a bigger disc on top of a smaller disc. So this is not allowed. So based on these 2 conditions, we are required to shift the tower from this peg to any of the other 2 pegs using a minimum number of moves. So I'd like to take you along with me on this journey of solving the Tower of Hanoi puzzle and looking at many other interesting variations of this puzzle. So I'll be using a PowerPoint presentation. So here we are, the Tower of Hanoi puzzle. I've already described the conditions of the puzzle to you. In this picture, you can see a puzzle where the pegs are linearly arranged, but it is the same as what I have shown you earlier. The conditions remain the same. Only one disc can be moved at a time, and a bigger disc can never be placed on top of a smaller one. So I would urge you to try and play this game yourself. You can try and find certain animations available online, or you can try and create some cutouts to help you explore this. So another thing could be to simplify the problem. That is, you play with a lesser number of discs and you try to find a pattern. So instead of playing with all 6 discs at a time, maybe you could just try and see what happens if there were only 2 discs. So for example, if there are only 2 discs on one of the pegs and I need to shift it to any of the other 2 pegs, I need to remove the red disc first and then the black disc to another peg and then put the red disc on top of that. So this took precisely 3 moves, and 3 is the minimum number of moves required to shift 2 discs. Now you can increase it to another disc and see what happens. So if I need to move these 3 discs, what I need to do is I need to shift these 2 discs to another peg, but I can't do it together. So I shift the red one here, the black one here, the red one on top of the black. The lowest disc comes here. Here, the black comes on top of the biggest disc, and then this. This took me 7 moves. So we will explore further, but in order to take you through the exploration, here are 2 tasks. The first task states, let n represent the number of discs and t of n the minimum number of moves. Try to compute Tn for n going from 2, 3 and 4. So for 2 discs, we have seen that the minimum number is 3. And for 3 discs, it is 7. Do you detect any pattern as n increases from 2 to 3 or from 3 to 4? In other words, can you express t of n, the minimum number of moves for n discs, in terms of t of n minus 1, which is the minimum number of moves for n minus 1 discs? Let us look for a recursive rule. Further, we would like to find an explicit formula or a rule which gives us the minimum number of moves t of n in terms of n. So now here we have a table. On the first column, we have written the number of discs, and on the second column, we need to write the minimum number of moves. So you've seen for yourself that for one disk, of course, it's a trivial case. We only need one move to shift a single disk. For 2, the minimum number of moves was 3. And for 3, the minimum number of moves was 7. Okay, so let me quickly show you. For 2 disks, as we said, the 3 moves are as follows. Here there is a blue and a red disk. The blue disk is in the first move is shifted to the middle peg. In the second move, the red disk is moved to the third peg. And then in the third move, the blue disk comes on top of the red disk. So there are 3 moves which we have already seen in our wooden model. For 3 disks, it was 7. So repeating on this diagram, if I add one more disk, let us say I add one more disk here, how would I make the moves? So the top 2 disks can be shifted to the middle peg, let us say, using 3 moves, because we know that the minimum number of moves for 2 disks is 3. The lowest disk can be shifted to the last peg using 1 move, and then these 2 disks which were in the middle peg can now be shifted to the third peg using 3 moves. So it is a total of 3 plus 1 plus 3, which is 7. What happens if we had one more disk? What if we had 4 disks? So let me try and draw a diagram here for you. So on the first disk, I have 4 pegs arranged in a tower. When I need to shift these entire tower, first I'll have to release the top 3 disks. Suppose it is shifted to the middle peg, it would need 7 moves. The lowest disk can be shifted to the last peg using 1 move. And then these 3 disks which were in the middle peg can now be moved to the third peg using 7 moves. So this is a total of 7 plus 1 plus 7, which is 15. So for 4 disks, we would need a minimum of 15 moves to shift the tower. I hope this recursive idea is clear to you. In the next slide, this has been written out. So for 1 disk, we have 1 move, which is also written here. For 2 disks, we have 1 plus 1 plus 1, which is 3 moves. For 3 disks, it was 3 plus 1 plus 3, which was 7 moves. It can also be written as 2 into 3 plus 1. For 4 disks, it was 7 plus 1 plus 7, which is 2 into 7 plus 1. For 5 disks, it turns out to be 2 into 15 plus 1. So a total of 31 moves are required. A minimum of 31 moves are required to shift a tower of 5 disks. So if you look at these statements highlighted in blue, you will see a pattern here. So for n disks, the recursive rule is 2 into tn minus 1 plus 1. So the minimum number of moves for n disks is twice the minimum number for the previous number of disks plus 1. Now if you look at the minimum number of moves here, we need to find a formula for this. So for 1 disk, it is 1 move. So let me write it here. We can also write 1 as 2 raised to the power 1 minus 1. We can write 3 as 2 square minus 1, 7 as 2 cube minus 1, 15 as 2 raised to the 4 minus 1, and so on. 31 as 2 raised to the power 5 minus 1. So for n disks, it will be 2 raised to the power n minus 1. And this gives us an explicit rule for finding the minimum number of moves for any number of disks. Okay, so now here in this slide, you saw that this was a conjecture we made by observing the minimum number of moves. But we really need to prove this. And for proving this, we need to use the principle of mathematical induction. What is the principle of mathematical induction? It says, suppose that for each positive integer n, we have a statement Sn with the following properties. S of 1 is true, and if S of k is true for a positive integer k, then S of k plus 1 is also true. If these two conditions hold, then S of n will be true for every positive integer n. This is a statement of the principle of mathematical induction. It is something like climbing a staircase. Now, if you have to climb to the top of the staircase, you should be able to climb to the first step, which represents the situation of n equal to 1. And then we assume that if I can climb onto any kth step, then I should be able to climb onto the k plus 1th step. If I'm able to do this, then using these two conditions, I can actually climb to the top of the staircase. This is just an analogy to explain you the principle of mathematical induction, the steps of the principle of mathematical induction. Now, how do we apply to prove our statement that T of n, the minimum number of moves for n disks, is 2 raised to the power n minus 1. So this is the statement which we need to prove. So for the first step is to verify if this is true for n equal to 1, because only then we can start with the induction process. What does T of 1 represent? It is the minimum number of moves for one disk. So if I substitute n as 1 here, I get 2 raised to the 1 minus 1, which is 1. So this is true. Indeed, for one disk, it is one move. Now we assume the statement to be true for n equal to k. That is, T of k is 2 raised to the power k minus 1 for a positive integer k. Now that these are the two conditions of the principle of mathematical induction, I need to prove that T of k plus 1 is 2 raised to the power k plus 1 minus 1. For this, we use this condition, the step 2. So T of k plus 1 is equal to 2 times T of k plus 1, because this is a recursive rule which we have observed from the puzzle. And replacing T of k with 2 raised to the power k minus 1 and simplifying, we are able to show that T of k plus 1 is indeed 2 raised to the power k plus 1 minus 1. And this proves the statement of the Tower of Hanoi puzzle. So now I'll stop sharing for a bit and let us see if we try to do this for 5 disks. So there is a tower of 5 disks here, and according to what we've just discovered, we would need 31 moves to shift this tower from here to any of the other 2 pegs. So let's start. 1, 2, 3, 4, 5, 6, 7. So 3 have got moved with, 3 disks have been shifted with 7 moves. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. So indeed, 31 moves were required to shift a tower of 5 disks from one peg to the other. Now let us move forward and explore this puzzle in more interesting ways. So allow me to share the screen again. The Tower of Hanoi puzzle also leads to very interesting counting problems. One of them is, for example, in how many ways can 2 disks be arranged on 3 pegs? What about 3 disks? Can we generalize this and find the rule for a number of arrangements of n disks on 3 pegs? So let us see. In this, I have only 2 disks on one of the pegs, the black one, the bigger black one, and the smaller red one. Now, the black disk can be arranged on any one of the pegs, so the black disk can be placed in 3 ways. Further, the red disk can be also placed in 3 ways, although the red disk must always go on top of the black disk, but the red disk can also be placed in 3 ways. So the total number of ways would be 3 times 3, which is 9. So this is one of the possible states where the 2 disks are on the same peg, or this could be another state where the 2 disks are on different pegs. If we add one more, let us say we add one more disk, let us take the case of 3 disks, then we see that the lowest disk can be placed in 3 ways, the black disk can be placed in 3 ways, and the smallest disk can also be placed in 3 ways. So 3 into 3 into 3, there will be 27 ways of placing 3 disks on these pegs. Now, let us see the case of 2 disks and 3 pegs. If you look at the total number of arrangement, this picture represents the number of ways, the 9 ways in which we can place the 2 disks on 3 pegs. To identify these, we can follow the following convention, that we label these pegs as 0, 1, and 2. Let me do it for all of them just for clarity. And this will help us identify the states. So when both the disks, the bigger and the smaller one, are placed on peg 0, we label this state as 0, 0. Remember that we are using 2 digits to represent each state, where the first digit represents the position of the bigger disk and the second digit represents the position of the smaller disk. So here this is 0, 0. In this case, since both the disks are on peg 1, we will call this 1, 1. In this case, when the 2 disks are on peg 2, we will call it 2, 2. However, if you come here, the bigger disk is on peg 0 and the smaller one is on peg 1. So we can call this 0, 1. We can call this 0, 2. We can call this 1, 2 because the bigger disk is on peg 1 and the smaller disk is on peg 2. This becomes 1, 0. This becomes 2, 0. And this becomes 2, 1. So these are pairs of digits represent each of the positioning of the 2 disks on the 3 pegs. And this will be helpful to us in what we are about to do later. So let us see. We can develop something called Hanoi graphs, which are intricate, highly symmetric combinatorial graphs of the form. The symbolic form is HDP, where D represents the number of disks and P represents the number of pegs. In our case, our number of pegs is 3, so that is fixed. It is D which can be varied. Now let us see what happens in the case of only one disk. So in this case, we would be trying to create H13, where 3 is the number of pegs and the number of disks is only 1. Now suppose I place the disk in peg 0. It can be easily moved to peg 2 using only one move. Or the disk can also be moved to peg 1 using only one. Or if the disk happens to be on either peg 1 or peg 2, it can be shifted to the other peg using exactly one move. This idea can be represented using a simple graph as follows. So we use this state will be represented as state 0, this will be represented as state 2, and this will be represented as state 1. And I can use dots to represent these states. This will be 0, this will be 1, and this will be 2. And I join 0 to 1 because it is possible to move from this state to this state using exactly one move. So these can be joined using a line, which we call an edge in the language of graph theory. So in the language of graph theory, these points are vertices and these lines are edges. and we can connect them because a single move can take me from state 0 to state 2, from state 2 to state 1, and from state 0 to state 1, and so on. So this is the Hanoi graph H13. It is also referred to, these are also referred to as state graphs. A state graph is a graph whose vertices are legal states. Two vertices are connected by an edge if a single move takes us from one state to another. So this is the simplest graph, which is H13, the case of exactly one disk and 3 pegs. Let us see how to create H23. Now the diagram on the left hand side represents the position of the disks on the 3 pegs. And correspondingly, this is the Hanoi graph. Now let us see how we're going to go about doing this. This is state 0, 0. If I label this peg as 0, 1, and 2, both the disks are on peg 0, so this state will be 0, 0. Similarly, this state will be 1, 0. This state will be 0, 1. This state will be 0, 2 because the bigger disk is on peg 0 and the smaller disk is on peg 2. This will be 2, 1. This will be 1, 2, and so on. Let's take this case. This will be 2, 2. This will be 2, 0. This state is 1, 0, and this state is 2, 2. 1, 1. Sorry. So we identify these states, and it is possible to move from state 0, 0 to state 0, 1 in exactly one move because this disk is simply shifted here. So let us label these vertices of the Hanoi graph as 0, 0, 0, 1, 2, 1, 2, 2, 0, 2, 1, 2, 1, 1, 1, 0, and 2, 0. And these are joined. 0, 0 is joined to 0, 1 by an edge because it is possible to move from this state to this state in exactly one move. Likewise, it is possible to move from this state to this state in exactly one move. So we join this. All the legal moves are represented by an edge. However, from 0, 0, I cannot directly go to 2, 0, and therefore these are not joined. So this is an intricate and nice Hanoi graph, which we represent as H23 symbolically. And notice that H23 has 3 triangles, this one, and this one here. So it has actually, each of these is similar to an H13. So H23 has 3 copies of H13 in it. This is an interesting observation. How do we create H33? Now H33 should have 3 copies of H23. Now what I have shown you here is actually H23. 1 copy, 2 copy, and 3 copies. These are the 3 copies of H23. And if I join these, this vertex to this vertex, this vertex to this vertex, and this vertex to this vertex, what I actually get is H33. Okay, moving on, what do we observe? We observe that this one is H13, this graph here, 3 vertices labeled 0, 1, and 2 in a triangular manner. H23 is here. It has, so H13 has 3 vertices. H23 has 9 vertices, and H23 has 3 copies of H13. So this is an H13, this is an H13, and this is an H13. Similarly, H33 has 3 copies of H23. So this is an H23, this is another H23, this one, and this one is another H23. So H33 has 3 copies of H23, and H23 has 3 copies of H13 and so on. In general, HN3 will have 3 copies of HN-13. Now, in this particular section, we will be looking at the 2-color challenge. So let me share the screen and tell you what that is. So as you know, the regular Tower of Hanoi puzzle has 6 discs of 6 circular discs of reducing radii which are arranged on one of the pegs, and this puzzle has 3 pegs. Now in this variation of the puzzle, we have to make 2 separate towers, one of each color, using a minimum number of moves. The 2 conditions remain the same as the original problem. Only one disc can be moved at a time, and a bigger disc can never be placed on top of a smaller disc. So if this is the original configuration, ultimately we want the configuration to look like this, where we have the black discs on one peg and the red discs on another peg. But we have to do this move using a minimum number of moves. So as the diagram also indicates here, there is the middle peg has the disc arranged in alternate colors, and ultimately we would want an arrangement which looks like this, where the white discs are on one peg and the black discs are on the other peg. Okay, so let us try and see how this can be done. Now clearly, if there is only one disc, then there is nothing to be done. Because there is only one color involved. If there are 2 discs, then only one move is required to separate the 2 colors. Let's see what happens if there are 3 discs. If there are 3 discs, then this could be one move, 1, this is 2, and this is 3. So for 3 discs, the minimum number of moves required to separate the colors is 3. Now let us see the case of 4 discs. Now I have 4 discs, so I do 1, 2, 3, 4, 5, 6. So let us record the minimum number of moves required in this table. So for 2 discs it was 1, for 3 discs it was 3, and for 4 discs it is 6. And you can keep on adding more and more discs and try to observe what would be the minimum number of moves required to separate the 2 towers, separate the tower into 2 colors. So here is an interesting, if you've been able to play with the puzzle, you will see that these are the numbers. For 1 it is simply 0, for 2 it is 1, for 3 we have seen it requires 3 moves, for 4 discs it requires 6 moves. For 5 the number of moves is 13. This is a little more challenging. For 6 it's 27, so it seems to increase very quickly. Now to see a pattern in the minimum number of moves, because we would like to generalize this for n discs, this is how we proceed. We try to write the minimum number of moves in powers of 2, just as we did in the original problem. So 1 can be written as 2 raised to the power 0, 3 can be written as 2 plus 1, so that is essentially, so we are writing here 3 as 2 plus 1, which is the same as 2 raised to the power 1 plus 2 raised to the power 0. 6 can be written as 4 plus 2, which is 2 square, and plus 2 raised to the power 1. Similarly, 13 can be written as 8 plus 4 plus 1. And in powers of 2, it is written as 2 cube plus 2 square plus 2 raised to the power 0. Going on to 27, we can write 27 as 2 raised to the power 4, which is 16, plus 2 cube, which is 8, plus 2 plus 1. And once we have done this, even if we go on to 107, which is the minimum number of moves for 8 disks, we can write it in powers of 2 as 2 raised to the power 6 plus 2 raised to the power 5 plus 2 cube plus 2 square plus 2 raised to the power 0. We observe an interesting pattern here that the first exponent in the path, the highest exponent of 2, the highest power of 2 in the sequence is 2 less than the number of disks. That gives us a hint that for n disks, the highest power of 2 should be 2 raised to the power n minus 2, as you can see here. The next power is 1 less, so it is 2 raised to the power n minus 3. And then after that, there's a missing power. For example, for 8 disks, for 107, you have 2 raised to the power 6, 2 raised to the power 5, but there isn't any 2 raised to the power 4. So there's a missing power. So in these sequences, there's some missing powers of 2. If you record them correctly, you would be able to write the nth term for n disks, that is the minimum number of moves for n disks. Now, if you write the same numbers in binary form, so for 1, it is simply 0. For 1 can be written as 1 in binary notation. 3 is written as 1, 1. 6 is written as 1, 1, 0. 13 can be written as 1, 1, 0, 1. 27 can be written as 1, 1, 0, 1, 1. Just to show you quickly how this is done, let us take the case of 13. If I want to know how to write it in binary notation, I simply divide 13 by 2 and I get 6, and then there's a remainder of 1. Then I divide 6 by 2, I get remainder of 0. Divide 3 by 2 again, and I get a remainder of 1. And reading this backwards, 1, 1, 0, 1 is what we have for as the binary notation of 13. So when we look at the binary notations, we have 1, 1, 1, 1, 1, 0, 1, 1, 0, 1. For 27, it is 1, 1, 0, 1, 1, and so on. We see that we have repetition of 1, 1, 0. And this is repeated n minus 1 times for n. So this gives us a way of generalizing the two-color challenge of the Tower of Hanoi puzzle. So if you are interested to explore further, here are some resources. The first one here gives a nice animation of the Tower of Hanoi puzzle. So you can explore this, and you can increase the number of pegs, or you can increase the number of disks and explore. And here are 2 articles based on the Tower of Hanoi puzzle. With this, I take your leave. I do hope you have had a wonderful time exploring the Tower of Hanoi puzzle. Thank you very much.